All right, well, thank you all for coming here, and for those of you joining online, thank you for doing so. Those of you that don't know me, I'm Bruce, and I'm going to be talking to you today about, as Zach mentioned, a new advanced development concept that we've been looking at in conjunction with Intecsea. So I'll just take you through quickly the main points that we'll be going through in the presentation. Firstly, when we look at these new development concepts, we're doing it primarily through the idea of modeling. In particular, we use the OLGA extensibility framework for that, which is an API that Schlumberger has built, which allows us to plug in to OLGA directly and make modifications for hydrate formation within the program. So what we've done is to take the extensibility framework and build our own gas-dominant hydrate plugin, which Tom Charlton, who's in the audience, is the one that built that. So have a chat to him afterwards if you'd like. And we've used that to simulate a 250 kilometer long flow line, which is normally producing about 500 million scuffs per day. And what we're going to look at is two different options for that. Firstly, there's dual 18-inch tiebacks, which is a fairly standard sort of solution, but we'll be taking a look at the concept of underinhibition and see what we can achieve with that. And then secondly, we'll take a look at our advanced development concept, and this is basically subsea separation. So in that case, you wind up with two lines, firstly a gas line, and then separately a smaller pure liquid line. And what we find is that by approaching this particular concept and then adding in a few new and interesting things, so these thermoplastic composite pipelines with anti-agglomerants allow us to do some interesting things with the liquid phase. The gas line, we'll see that the separation actually offers us some substantial advantages in terms of a reduction in the back pressure and therefore a reduction in the amount of THIs that are needed. And ultimately what we wind up finding is that there is at least potential with local chemical storage and local power solutions as well to wind up eliminating umbilicals from the system. So firstly, the work that we do here, it sits primarily within the modeling domain. You can see here the whole list of different experimental apparatus and modeling techniques that we have available in the Center for Long Subsea Tiebacks. We're going to be dealing, as I said, primarily with modeling through OLGA and the extensibility framework. But one important thing that we always keep in mind within our modeling is that it really has to be backed up by experimental evidence. So the gas dominant plugin was validated against the Hydrate flow loop, which you can see down here. And some of the results on the thermoplastic composite line were taken using a micromechanical force apparatus. And Max Conroy, who is up next, will be telling you a little bit more about what exactly we did there and what that all means. So the overall aim of the Center for Long Subsea Tiebacks, as you might guess from the name, is to enable us to actually build these things economically and to try and look at new ways and new development concepts to deal with, in particular, hydrate formation. So what we can see here is just a little profile plot. So you've got the volume fraction of hydrate on the ordinate here, and on the abscissa, this is just our length from the wellhead. So if you think about water flowing through a pipeline, initially you're outside the hydrate equilibrium region, so it just flows as pure water. Once we hit that equilibrium region, it can begin to convert into hydrate. And we can get effectively one of two things happening. Either it'll form a deposit, in which case it winds up growing on the wall. As that annulus begins to narrow, we see an increase over time in the shear stress on that deposit. And in principle, we can start to look at experimental metrics for how likely our sloughing is going to be in conjunction with that modeling estimate of the shear stress. So the model isn't quite there yet, but certainly this is the direction that we're moving in. And then secondly, we can also look at what happens in the liquid phase. So if you have a whole bunch of hydrate particles flowing along in your liquid, that slurry is going to become quite viscous over time. And that's what we can see in this little figure down here. Our relative viscosity increases. That makes it harder to flow our fluids. So what this lets us do is it gives us two mechanisms for actually depleting the energy in a pipeline. Either you've got a narrowing annulus or your fluid is actually becoming thicker. So really that lets us get at the idea of these mechanistic plugging predictions. And what we mean by that is that the actual simulator is built in such a way that we can see the depletion of that momentum energy, and we should begin to see the fluid physically come to a halt within the simulation. So the way that's put together within our gas dominant plugin, We've just got a little schematic here. You can see we have some simulation framework. This can be either OLGA, or we've recently done some work with wood to introduce this to Virtuoso as well. And effectively, what you wind up doing in these simulators is you divide your pipeline into a whole series of different sections. Within each one of those sections, we wind up running our gas dominant plugin. Now, firstly, we work out, are we in the equilibrium region? Then we can, if we're outside, we might have hydrate dissociating. If we are inside, then we can get hydrate growth. Now, where does that hydrate grow within our simulator? Well, we have 4 different interfaces that we care about. So firstly, there's this gas-water stratified interface here. This is the bulk interface between the phases. We then have 2 film growth interfaces. So the gas wall interface around here and the liquid wall down the bottom. Now, these tend to grow very slowly. And the most important interface by far is of all of these little droplets here. So these are entrained droplets that are picked up by the gas phase moving over the liquid and transported and converted. So the question is, what happens to these droplets in particular? Once they're entrained, they can either be advected along the pipeline, they can fall back into the liquid and be carried along in that slurry phase, or they can wind up sticking to the walls, and then they will form a deposit, as we saw in the previous slide there. So the integration with OLGA, it's actually quite simple. The way it's set up now, we just provide you with a little extension file. OLGA has a nice little button which says install. You go ahead and do that. And then you can effectively just run the extension and see what the impact is in terms of hydrate formation on your system. Now, this is quite advantageous to us because Schlumberger has really optimized the way the program works with the extensibility framework. So you won't see that much of a decrease in your simulation times by using the extension. And finally, getting back to that point, the really key thing here is that it lets us look at the effect of the hydrate formation. And we'll see a couple of examples of that throughout the presentation later on. So just to quickly recap for you what we've seen over the last year or so of presentations on the extensibility framework. I believe in July, we took you through the way that the extension integrates with OLGA's THI tracking. And so as you form hydrate, you concentrate the thermodynamic inhibitor in the aqueous phase, and you wind up getting this sort of self-inhibition effect. In November, we took a first look at these thermoplastic composites. We introduced the concept of it, but we were primarily targeting main production lines at that time. And what we'll be looking at in this presentation is, of course, the idea of subsea separation. So effectively what we're doing here is we're partitioning that hydrate problem separately into a gas phase and a liquid phase, and we want to deal with hydrates separately in each of these because you have quite a different solution depending on what phase you're in. So firstly, in the gas line, what you wind up seeing is that because you don't have liquid to push along in that line, you wind up reducing the back pressure quite substantially, up to tens of bar. And also, if you have really good separation, then you can actually reduce the amount of THI that's required as a baseline just because you are starving the system of water. In the liquid line, where previously we talked about main production lines, we're now talking about these much smaller liquid umbilicals on the order of a few inches, maybe up to 4 inches. And this is now tractable because this is where the technology actually is at the moment. So these are things that can be deployed. And ultimately, once we start combining these different technologies, we can, again, get at this potential to eliminate meg umbilicals, power umbilicals, these sorts of things. So we can simplify our systems quite substantially. Now, to take you through quickly that advanced development concept and just run down on exactly what it entails. So it's built primarily around the core of this pseudo dry gas. So this is a technology from Intecsea. You can see a diagram of what this would look like subsea. And this is a little video of a low pressure system being tested. So you can see the liquid and gas comes in here. We have the separator and we partition off a relatively dry gas line here, and then the liquid flows on that smaller water line there. Now, the advantage of these things is that they are more or less continuous, so you can pig your gas line quite happily. As I said, we get a reduction in that back pressure on the gas line, so that's all very advantageous. And then we separately have a more complicated liquid return system down here. This tends to be a much smaller ID line, and it winds up being boosted with a series of different pumps in order to get it back to shore. So within that liquid line itself, the baseline design had been to use carbon steel, but we've had a number of other projects with airborne come online, and this suggests the use of these composite materials instead for that liquid return. Now, I won't go into too much detail because Max is going to cover that next, but essentially these were originally designed to deal with corrosion, but Airborne has come to us to talk about the possibility of mitigating hydrate, and in particular, the ability with the use of an anti-agglomerant to completely prevent the buildup of hydrate within these pipelines, so prevent it from sticking to the walls. Now, the problem, I guess, with anti-agglomerants traditionally has been that these things tend to be quite ecotoxic, and that's why we've been going through a number of projects with Shell and Woodside and CSIRO, looking at the idea of these biocompatible AAs. So whereas a typical Gulf of Mexico type AA will be toxic at, or have an EC50 of less than 1 mg per liter, the AAs that we're targeting have an ecotoxicity of at least 10 mg per liter, which is the Norwegian standard for a non-toxic anti-agglomerant. And what these effectively do, firstly, these are now non-toxic. And if we take a look just at this figure down here, we're basically looking at the yield stress as a function of the amount of hydrate that you've got within the system. So how hard is it to push the hydrate along our pipeline? And in red is what happens when you don't have an anti-agglomerant in the system. But when you do dump one of these AAs in, you can see that we really reduce the amount of energy that's required to push material along the pipeline. So by combining those with our thermoplastic composites and then using the idea of subsea separation, we wind up at our advanced development concept. So to look at a comparison of how this performs versus a more traditional solution, we'll just go through a case study now. And the case study is going to be in two halves. So you can see here we've got the bathymetry of our test system or our example system. So it's a 250K tieback. In black is the bathymetry. In blue is the water temperature. And the baseline, I guess, is our dual lines. You can see it's very simple. You just have two 18-inch flow lines. These are multi-phase pipes. And we'll look at what happens when we underinhibit those things by a little bit. And the second is our subsea separation. So again, we have a series of separators along the line, pulling out progressively more liquid as we move along. And then we separately bring the liquid back to shore. Now in this particular case, we've gone with 6 different pseudo dry gas units, and you can see the little red dots indicate the locations here. Now what's actually in the pipeline? Well, we've got the composition here, and we've got a little PT diagram with our VLE curve here. So at the manifold, the entrance to this, our inlet condition is a 2K vertical well with a linear inflow performance relationship on it. This then cools rapidly, and we slowly move along till we get to our processing facility. The boundary condition there is just kept at 75 bar, more or less to match what you would see at the inlet to one of your LNG facilities. Nominally, this entire system should produce 500 million scuffs per day. So in the case of the dual tieback, you expect to see 250 down each pipeline. In the PDG system, you wind up with all of that going down the gas return line. And as we said, we're looking at 2 different cases, our dual carbon steel return line or our 24-inch carbon steel return with a liquid line on it as well. So if we put in the hydrate curve, you can see, unsurprisingly, that as a baseline, we wind up within the hydrate equilibrium region. The interesting thing is what happens if you look at the idea of perfect thermodynamic separation. So this might be if you've got a really, really efficient separator and you're looking right after its location, you can get up to about 10 degrees inhibition as a thermodynamic effect. Now, in reality, you're not going to see it go quite this well, but there's some potential there just for a natural thermodynamic retardant to hydrate formation. And the questions that we're really going to be asking with 2 sets of simulations are, firstly, for our dual tiebacks, how do these self-inhibiting systems behave? And then secondly, in the case of the pseudo dry gas, what advantages does that give us for hydrate management? So firstly, we'll take a look at the dual tiebacks. And what we're going to be showing is just a series of videos. So these are all going to be profiles which move with time. You can see here's our flow line length on the bottom. In black, we have the standard gas flow rate in million scuffs per day. So this is the dual tieback. We expect it to start at about 250. In red, we have the effective diameter of the pipeline. And in blue, we have the hydrate fraction. So as we start that playing, there we are. You can see we start off with no hydrate in the system, flowing quite happily. We get this severe deposit, which winds up forming at the inlet in less than a day. And you can see that as that forms, it chokes off flow and the gas flow rate reduces down to about 100 million scfs per day. And what you wind up with are these secondary deposits in blue. Now these aren't on the pipeline wall, and you can tell that because they're not matching with the red up here. These are just liquid deposits which have settled back into low points. So what's effectively happening here is you get a primary deposit that chokes out the liquid system, and then you get these secondary deposits which are caused by bedding. Final thing to note on this simulation is that while the liquid line is most definitely stalled, we aren't seeing the gas reach zero. So that's an important thing to note when you're running these sorts of simulations. This system is definitely plugged, but it's just a limitation of the simulator at the moment that you don't see the gas rate itself go to zero. So this is a 250K line with no inhibition whatsoever. It shouldn't be particularly surprising that things don't go particularly well. If we look at the other end of things, what happens when we do a little bit of underinhibition? So we need 41 weight% meg to fully inhibit this system. This is going to be a simulation with 35 weight% meg. And again, we're looking at flow line length for a 10-day simulation. Red is once again our effective diameter. Blue is once again our hydrate fraction. And this time in black, we have our inhibitor mass fraction. So the initial condition here is that we have a fully inhibited system. As we go ahead and play the video, you see that we reduce the amount of meg which is being put into the system. We come into the hydrate equilibrium region, and we wind up with these three deposits that you can see growing very slowly on the wall here. Now, there are several deposits. They are growing incredibly slowly. So you get a 1% reduction in the internal diameter over the course of 10 days, and that does not do anything to your production rate. So this is actually quite encouraging because it means that you might be able to operate for longer periods without actually having to manage the system too hard. So if we go ahead and fill in the blanks between no inhibition and full inhibition, that's what we have on the next slide here. So you can see black this time is diameter reduction. Green is our flow rate reduction, so 100% is completely blocked and no flow. And we have our fully inhibited condition over here at the 40, and we move to no inhibition over here. So looking at this, we notice a couple of things. Firstly, if we do a little bit of underinhibition, the system seems to behave reasonably well. So it's more or less linear. You might be able to control what's going on here. And potentially you can look at pulsing your meg rate on the order of weeks or months, and you can flush that deposit out through the pipeline and then just reset yourself to some initial state. We then have this region with extremely nonlinear behavior over here. And this is really important because in the linear sort of region here, we might see blockage over the course of weeks to months. Within this region, it can be on the order of hours. So especially if you're playing within this region here, you need to be very confident as to how fast you're actually forming your hydrate. And then also you really want to have a very good idea of exactly how much thermodynamic inhibitor you have locally. So this is where you need to look at something like online monitoring. That can be, for example, through Virtuoso or through OLGA Online, but something which will give you a reliable estimate of what your local THI concentration is. Now, on top of that, what you also need is to accurately understand where your equilibrium curve is. And that's something I think David is going to be talking about a little bit later, really having a good either experimental or modeling-based understanding of exactly where your equilibrium curve is, because that helps you dictate basically where you are on this line down here. Now, I assume everyone is wondering why on earth this happens in here. We actually decrease the amount of meg that we put into the system and things get better temporarily. So we have a nice little video here. Again, flow line length, the red is going to be the effective diameter. Again, black is the inhibitor mass fraction, but this time we've got our pressure signal in green. So this case, we initially have a fully inhibited system, and then we reduce the inhibitor to 5 weight%. So if we go ahead and play that, you can see that along the pipeline, we have this sort of long deposit, which winds up forming. And then we have this severe deposit at the inlet. So if you watch what happens with the pressure signal here, you'll see that it actually rises up quite suddenly and then it resets. So what is going on there? Well, as we saw, the simulator can actually predict a stalling of the liquid phase. So this primary deposit is firstly stalling out the liquid phase. That then trickles back down pipeline and it winds up melting out that deposit which caused the blockage in the first place. And now there's no deposit, there's no more pressure drop across it, the flow can restart. And this cycles again and again. I think it happens 2 or 3 times during this simulation, but it's an interesting little exercise that we can see here. So that's the underinhibited systems, and you can see that there is some potential to play around in that space. We'll look now at this advanced development concept. Again, through the lens of a couple of different videos. I think we have 4 here. Once again, flow line length, gas flow rate. It's a single gas line now, so our nominal production rate is about 500 million scf per day. And we are looking in red at the effective diameter, blue is the hydrate fraction. So we play the video, and the first thing you notice is that you get this really long deposit which forms along here. This is just a boundary condition effect. The system is suddenly allowed to go into the hydrate region, and we see this occur. The main thing, the main deposit that you see is this very slow growing deposit at the inlet here. And what we see is that this is growing a couple of percent over the course of the simulation, and you really don't see any reduction in the flow at all. What you do see is a significant reduction in the back pressure. So rather than 190 bar required to drive this system, you only need 140 in this case. So that has implications for the amount of time that you're able to produce the field, for example. And while it's not thermodynamically equivalent, you can say there's a performance equivalence between this system and a system which is underinhibited, in that you can look at how quickly is this deposit growing, and you can compare that to our underinhibited cases. So, this is quite a promising prediction for our gas line. Looks like we may be able to play with that and manage our hydrate quite nicely there. The next question, of course, we're partitioning the advanced development concept into a gas and a liquid line. So what happens within the liquid line itself? So we're going to look in the next few slides here, instead of a gas production rate, we'll look at an oil production rate, and that's in black, and then a relative viscosity in red. And I should note that because we're dealing with a pure liquid system now, we've switched over from using the gas dominant extension to using CSM-HyK. And I believe Luis Zerpa will be giving us an update on the latest in CSM-HyK in 2 talks time. So if we play this video, firstly, we should note these little bumps here. This is where you have your separators. What you wind up seeing is that very quickly, because the curve is coming up and then plateauing, this is basically indicating that all the water that is in the system is converting fairly early on. We find that to actually drive this liquid system, we need a 400 bar pressure at the inlet. Now, this is actually kind of advantageous because it means that as we move along the line and pressure drops, we don't wind up going into the gas phase. So it keeps the whole thing in a single phase, but it requires pumping to do so. Now, we should note that the viscosity that we wind up with, a value of 60 or so, experimentally, we'd identify this as being quite a high-risk region. So you can see it's not affecting the flow rate too much in the simulation, but experimentally, we've seen that this sort of thing can be a problem. And so as a result of that, the baseline design for the pseudo dry gas system said, well, okay, if hydrates are going to be a problem in the liquid line, then what we should do is to take a thermodynamic inhibitor and inhibit this much smaller line. It's smaller, you'll require less THI, and we should save on the system overall. But what we've done in our advanced concept is to say, well, okay, can we take this a little bit further? And that's where we get at the idea of putting in an anti-agglomerant. So we'll show the same simulation again, oil flow rate and relative viscosity. And the first thing that we should notice is that rather than coming up to a value of 60, we're coming up to a value of 5 or so. So this now puts us in that low risk region identified experimentally. What we see is because the viscosity is lower and we're actually coupled into the flow engine, we see either an increase in flow rate or a reduction in the required driving force. So that's potentially saving on your pumping requirements. And also, we're in the low risk region, we may be able to eliminate THIs from the line. So the conditions to get at this particular simulation, we have a water cut on the order of 10%, and we have a lot of light ends in here because it's a condensate flowing through, there's a whole pile of methane. So what you wind up with is that in most of these simulations, you see that the liquid water does fully convert, and that's just a fairly typical result. So I'll show you one final video, and this is going to be what happens when you have a lot of water in the system. So you can see we're at 80% water cut. Again, red is relative viscosity, black is our flow rate, and this time green is our pressure. So if we go ahead and play that, you can see that hydrate forms, our viscosity goes straight to a value of 4,000. This should indicate that something bad is about to happen. And you can see that our oil flow rate here is quite low. And in fact, as the simulation goes on, you wind up seeing that it reduces to 0. And the associated pressure signal with that is just flat pressure. There is no driving force for our flow. And what we typically see is that if we get about 20% hydrate within the system, this is what happens. And the implication for that is that you can either have these sorts of systems working when you have a relatively small amount of water, so 10, 15% water cut, or a lot of water and not much condensate. Because if you're only getting a small amount of gas coming into that liquid line there, then you wind up being gas limited rather than water limited. And so you keep that hydrate fraction less than 20-ish%. And again, just like to show this because it's coming back to that message that we're simulating the effects of hydrate formation using these simulators. So I have shown you the conclusions before. I just have one more slide, which is the way forward. Where are we going with the extension from now? And essentially what we want to do is to look at improving our water dominant mechanics. So we're going to again look at the effect of what happens when we get hydrate formation in the water system. That's been validated experimentally through a collaboration with Oilfield Technologies and their HAL flow loop. So we have a PhD student working on that. And then we also have done some work with the Colorado School of Mines in their high pressure water tunnel, looking at trying to clarify what the surface area of bubbles in these systems looks like. And then the second major thing next year is we want to take a look at the idea of hydrate nucleation modeling and trying to get some way of describing that within the OLGA extension itself to include probabilistic nucleation. And this should be something that we do for systems which have both THIs and KHIs. And for those of you that would like to work out how it is that we're actually going to do this, I suggest you stick around for Vincent Lim's talk because he is the expert here on these systems. So that is the end. Thank you very much.